Action. Alright guys, so here we go. We're going to talk about time dilation today. So, as I mentioned previously, and in my previous talk about the whole formation of stars and the collapse into black holes do this crazy thing where they pull in a lot of gravity because of how dense they are, and because of how dense they are, and things start moving close to the speed of light, the closer and closer you get to them. That's pretty intense. And you've seen this, the best example, and we're going to hit on this, and I'm going to give you the heads up ahead of time. If you haven't seen Interstellar, I'm going to be spoiling that movie for you, because Interstellar does a really great job of explaining both black holes and time dilation. And it's also the most culturally relevant example that I can give somebody. So, the way... wrong screen. There's my screen. So whoops, nope, that one. So in the popular myths that we have about a light speed work like this, we've got your two classic ones. If you take your regular concepts of like Star Trek and Star Wars, the idea is you hit light speed, you go past it. It's technically Newtonian physics, the theories that Newton would have, which is, well, sure, great. Light goes at a certain speed, but why can't something go faster than light? And that's why we get warp 1, warp 2, warp 3, warp 4. Or you get, which is what your Star Trek thing. Or you get Han Solo, who's like, it'll make 0.5 past light speed. Might not look like much, but she's got it where it counts. Like, both of those are the concepts that, oh, you just go into warp and you're halfway across the galaxy. But in contrast to that, there's some kind of schmuck by the name of Einstein who kind of disagrees with that whole theory, and he's more bent on this philosophy of Interstellar. And the concept behind travel in Interstellar is the fact that to travel long distances, you either, one, have to spend a really long time in space, and so you go into some form of cryostasis. Like if you've seen the movie Alien, everybody's in a cryo sleep chamber, and then when the ship kicks on, it like reactivates and wakes the people up. Prometheus, which is actually a prequel to Alien, does the same thing. Interstellar does a mix where to get to destination 1 before things start to get really fun, they go into a cryo sleep. They go into a bag that gets put into water inside a machine, and then it freezes down and slows down the metabolism on the person, so they're essentially in stasis. That doesn't have anything to do with time travel. That's all metabolic. But the other concept is that when you travel into weird anomalies that are going to mess with time, so you get too close to a black hole, which has a strong gravitational pull, or if you end up going through a wormhole, which is essentially a distortion that's caused by a twisting of space, which could be caused by a black hole, both of those really start to warp time. And so in the movie Interstellar, the closer you are to the black hole, the closer you are to gravity, the more time slows down. And so one of the planets that they go into in Interstellar is so close to the black hole that every hour on the planet is about 5 hours in real life to everybody else. Not 5 hours, 5 years. It's something pretty intense like that. And of course you're watching the movie and you're like, okay, movie magic, that's what they said, so that's what we're gonna go with. But the way that plays out in Interstellar, and again, this makes for good comparison. Sorry to ruin the movie if you haven't seen it. If you have seen it, you will agree with me. It's both an amazing film, a powerful film, and a really good soundtrack. In fact, if I could, I'd be playing that the whole time I was doing this, but I can't. I just listened to it while I reread all my notes. So, you get this example in the movie. At this point in time, again, spoiler alert, I'm going to assume that we've all seen it, or we've politely left and gone to watch the movie, and then you're going to go ahead and just rewatch this tomorrow after you've seen the movie and said, wow, thank you, Gator, for that experience. But in the movie, we have Matthew McConaughey's character sits down with his daughter to be like, hey, I'm going on this trip. He knows there's going to be time dilation involved. He knows that that he's going through a wormhole, they're going towards a black hole, that this is going to be a risk. He thinks he's coming home, but he doesn't know how long it's going to take. And he even makes the comment of, with me going and then coming back, yeah, it's right there. It's like, by the time I get back, we might even be the same age, you and me. But time dilation's kind of sucky because it's when you start looking at percentages in terms of the percent of how close you are to light speed, it doesn't take a whole lot in terms of percentages to accelerate in human years the experience you're having. So of course, by the time he finally gets back to see his daughter, she's a lot older, a lot older, and like a lot older. I think they make a comment when they find him to say, like, dude, you're like 147 years old. But both of them have been either traveling or in cryo or in time dilation, all these different scenarios. And it's super duper kind of confusing as to like how old people get, and because every human life is only 80 to 90 years on average. Whereas when you're talking about stars, like star formations, we're talking literally billions of years. I think the solar, I don't remember the number, but I think the universe has been around for like 13.7 billion years. We're talking big numbers with lots of zeros. Us humans only get 1 0. That's it. So yeah, you get the full arc where they leave, or he leaves, and then he comes back because he went on a huge travel and he came all the way back. He stopped aging, but she continued to live her life all the way through. And this starts to bring in the question of like, how does, because if you go off of Isaac Newton, the guy who the apple hits his head and all that fun stuff, if you go off of that theory, he should just travel and he should come back. It doesn't really matter. It's still going to take the same amount of time. Why is there warpage in time? Why is what is this whole theory that light is going to be going at a different speed? And the whole theory is based off of, I go to sleep now and rewatch this next year. All right, take care, Cooney. So the question you have is, all of this theory of relativity is based off the idea that light, the speed of light doesn't change, period. It's a constant. And that because it's a constant, you can't go faster than it. And that seems like, for us here on Earth, that doesn't make a whole lot of sense. Because then the questions start to come in like, well, how do we know that? Do we just say, hey, let's play with this rule and see what that does? Or like, can we actually prove that? And we can. The thing is, we can, and we have. And when I heard that in the videos and the readings I was reading, I didn't like that answer. I didn't like the, oh yeah, of course we tested it in the lab and we saw it, we could see the numbers. It's like, okay, that doesn't sell it to me. Explain it to me in a way that sells it to me that light is a constant, no matter what. And the explanations I got were pretty good, and I will explain them a little bit more pop culture wise for you too. So, let's see. There have been tests, and one of the first things I was skeptical about was, I know that there have been tests where they say that like light going through a medium goes slower and they can slow down light and you can watch it move, and that's actually not true. What you're seeing is light itself is still traveling at the same speed, but when light enters a medium, it creates a refracted image of itself, and you're seeing that refraction. You're also seeing like the Doppler effect when a car goes by and goes like, that's a stretching of sound waves. And in much the same way, light can be, its wavelengths could be warped as well, but that stretches the wavelength, but the wavelength itself still is going at the same speed. So that explains why we can have color changes into different spectrums of light. So like when the sun goes down, instead of being bright white up above, it gets over here, it's red. It's because it's working its way through the medium of all of the atmospheric haze. But it doesn't, even though it's stretching out the light wave, it's not actually slowing down the speed of light. But the example that I heard that was really interesting, and they used a horse and buggy, which doesn't doesn't make as much sense because it's not going that fast. But is, if you think about it like this, a lot of it has to do with relativity. If you are standing on, in this example here, if you were standing on Earth and you shoot a laser that goes the speed of light, and then you have a guy who stands on a ship and he fires a laser, he should be able to, his light should be able to be traveling faster than the other light, and that's not the case. They still seem to travel at the same point, at the same speed. Otherwise, what scenario you would get is if you saw an explosion, theoretically, because in this scenario, because Trinity is coming towards us, if she was traveling faster than the speed of light, she would be seeing an explosion all the time that we would never be seeing because she's outrunning it. So theoretically, according to that theory, because if she had a laser and she was shooting that laser and coming at us, and there was a laser that is the explosion, the light from that explosion, theoretically, as long as she is coming forward at us and shooting a laser, that laser should always hit us first. So if she's going at at speed of light, and she fires a laser, that laser light should outrun the explosion light. So we'll start seeing her laser light forever before the explosion actually ever becomes apparent to us. That doesn't make any sense, does it? No, we see her shooting a laser and the explosion at the same time because light is constant for all observers. So if it helps to see it at this angle, you can kind of picture it the same sort of way, where Morpheus, the guy who doesn't have the tether to his body, is jumping out towards Neo. Now, if Morpheus took a picture, was jumping out and the explosion was behind him, and then he also was flashing a light, according to Newtonian physics, that light would hit Neo before the explosion did, because it's going at the speed of light plus Morpheus towards Neo, and that's just not how that works. I'm hoping that much makes sense. I can give you one last example that might culturally make sense. Let's say a sun blows up, or like a star killer base. Theoretically, if the Millennium Falcon was flying towards us fast enough, they would escape, and they were shooting light. The light that they were shooting would go faster than the explosion, and theoretically, if you're going at the same speed as the Millennium Falcon, you would forever only see his light, and you would never see the explosion. It's weird. It's really kind of weird. But when you think about it, we don't see that. We see the explosion and the flashing light at the same time because it's something bad at the same time. So, how do we explain this in a way that doesn't, to go from weird to not weird? If you can kind of accept the fact that because we don't experience what I just explained, that we see that when shit blows up and lights are flashing, they happen at the same time. Not the light flashing coming at us happening first. Part of the reason for that comes down to this theory, and this is the diagram that broke my brain back in college. And the idea is, if you have this looks a little confusing, but I'll go to a simpler image in a second. The idea is, let's say you have a person who is on the bottom train is not moving, the top train is moving. Yep, that's right. So if you have a bouncy ball and you throw it and you're on a train that's moving, from your perspective, you just see the ball go forward and come back and you catch it. Okay, so all you've seen is a straight line back and forth. For a person who's standing on the side watching you go by, even though you throw it, let me do it this way, even though you just throw it and bring it back, from their perspective, if you throw it here and it bounces here and then you catch it here, what they see, they don't see this. They see a ball go like this and this. And But when you're talking about it not being a ball, when you're talking about it being light speed, you have to think about it this way. So again, in the example, if you were the top one, if you were a guy in a train car throwing a ball back at the wall, all you see is it goes forward, it comes back, forward and back. If an observer on the ground is watching you drive by bouncing a ball, they see the ball, it was here, you and the ball were here, you and the ball were here, you and the ball were here. But it's actually you and the ball were here, you threw the ball, then at this point the ball's there, and by the time you get here, the ball's here. So they saw a zigzag movement pattern, which is what the bottom pattern is. When you're talking about the speed of light, what you're saying is that the top person sees the speed of light go forward and backwards. And seeing how it took that amount of time to travel, it doesn't change the fact that the light went forward and backwards in a set amount of time. So down below on the bottom example, it's to the observer who's standing on the ground, that light still took the same amount of time. But if you look at it, a tilted line like this on a triangle, we all know that the longest leg of a triangle is the long diagonal. So if you have a perfect, you see the cursor if I do this? Yeah. So if you have, if your triangle goes here, 1, 2, and then 3, this line is going to be your longest one. But in this example, this is your normal line, up, down, up, down. So this line is shorter than this line. But then how do you account for that? If from the experiences that we've seen in life are true, that speed is always going the same speed or light is always going the same speed for everybody, but light made it from point A to point B in the same amount of time, regardless of whose diagram you're going off of. The only thing that can change, because the distance hasn't changed, and smiles and nods. The distance doesn't change, and the speed of light doesn't change. The only thing left to change is the amount of time that elapses for those two people. Kaiwago smiles and nods. Let me think. A very simple triangle works like this. One leg is 3, one leg is 4, the fifth one is 5. In terms of distance, so 3 inches, 4 inches, 5 inches. In example A, the person who's throwing a ball, he sees the ball go up 3, come back 3. So the ball has traveled 3, 3. For the person on the ground, if this is your 3 line and this is your 4 line, this line here, which is the same line here, because this is what the person on the car saw, this is what the person watching the car go by saw. If this is 3, this is 4, to the person on the ground, this looks like 5 inches. To the person in the car, the same distance looks like 3 inches. So the observer on the ground sees that ball travel 5, 10 inches, whereas the person in the car only sees it go 3, 6 inches. 3 and 3. Again, so if speed of light hasn't changed, and the distance hasn't actually changed, the only thing that can account to it when you start to look at your typical equation is time. It's the only way to make those two numbers match up the way they're supposed to. But that's where the fun starts. And so I got the equation broken down over here. And let me see what it says. Blah, 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 blah. Yeah, so speed equals speed, which is how fast you're going, is distance over time, which means how far you're going and how long it took you. And in this example, velocity equals the speed of light, and the speed of light is a constant. So if your distance doesn't change, which is d, and your c doesn't change, which is your speed of light, the only number left that's still a variable is your time. Brain broke. So this comes back down to the same Interstellar experience that we just explained. So husband and wife, she takes off, she comes back, he's old as hell and she's looking good. Oh, but there's, how does that work in the math? And the math gets fun. I'm not going to go into the math quite yet, but this is the basic simple equation to explain to you what the time difference would be for a person. So it'd be, I actually took this off a different video, so they had Ron and Dawn rather than the husband and wife. But the difference is just a variable that's determined by that scary looking equation, which we will get to in a little bit. But here's where its relativity gets fun. She leaves and comes back. That's her perspective. Or that's his perspective. But from her perspective, even though she's traveling, her perspective, he ends up going physically that far away and then physically coming back, even though she's the one who drove off and came back again. So it's sort of the same idea of like when you're sitting in a train, sitting next to cars, and one car starts moving and you're not paying attention, and for a split second you don't know whether or not it's your car or their car, and you get that weird vertigo. That's relativity right there, because it's hard to know. Your frame of reference is normally the ground, but if you're in space, it's hard to know who's moving in comparison to who. Because even if she's flying off and he's staying on the planet, he thinks he's stationary, she thinks she's taking off. But if somebody's sitting on the moon and watching all this, they look like they're all doing this in perspective to the moon. So it's like, well, who gets to determine what the stationary moment of time is? Who gets to determine what's the grounding point? And that's the whole point about relativity, is everything is relative to everything else. It's that whole idea of, if I hit a wall at 30 miles an hour, it's no different than the wall hitting me at 30 miles an hour, because it's still the same amount of impact. It's the shared movement. So there's like a lot of that physics crossover between relativity and normal stuff. But that's the question, is what's the frame of reference? It's the exact another classic example right here of frame of reference is Dr. Seuss. You have the Zacks. You have two Zacks. You have a east. Is it east? I think it's east and west. You have an east-going Zack and a west-going Zacks, and they come to a point where they meet. But who's coming towards who? Who's in whose way? So who interrupted the flow of the other person? You don't know, because relative to each other, they ran into each other and the other person was in the other person's way. So that's a fun example of relativity, because you can't determine who's the stationary point at this, because both characters are moving. So the way they broke it down is painful. It is super painful. And I'm not going to explain it all, because Polywoggles is already slipping and smiling and nodding. But the way to break it down is there's something called the Lorentz transforms. They are a series of equations that hurt the brain, and it took me about 3 or 4 times of re-listening to the same video and pausing and stopping and pausing and stopping, and then going back and re-watching the equations before it started to make sense. And the way they determined, the way they demonstrate this whole thing of like, well, okay, you have Bob and Gail and their perspectives, but that they're only relative to each other. What about a third party involved who's just watching the two of them move in relation to them? And so what they did was they said, okay, let's take 3 locations. You have point A at the beginning, which is here. Point 1 is where let's restart. So you got 3 locations. You have Gail's going to another planet. So location A is Earth. Location B is Gail going to the planet, and location C is Gail coming back from the planet. Because part of you is kind of like, well, if you age going that way, wouldn't you like unage coming back the other way? And it doesn't work that way. And it's like, but why? And so they've pretty much figured out what the time distortion would be at each of these stages using these equations to find out what A's perspective would be, what a person moving in B motion would be, and what a person moving in C motion would be. Like I said, it's a lot of painful math. And this is kind of what the Lorentz this is part 1 of what a Lorentz transform is. These are what the equations look like regarding what person 1 and person 2's position in space and position in time are in relative to each other. Then, on top of that, From that, you can get what the duration is of the two of them in comparison to each other, and then from there you can break it all down to figure out in relation to one person moving versus the other person moving what the total duration is for one person versus the other person, blah blah blah. Instead of explaining all of that in really, really great detail, what I'm going to do for you instead is I'm going to, wrong screen. I'm going to just give you the links. For anybody who wants to hear somebody who actually like went to school for this and knows what they're talking about, these are the videos I watched to get reference points. I'll end up posting these in my Discord at some point. And by some point, I mean like tomorrow or tonight if I go to bed early enough. But it is a guy explaining what this whole confusion of like, well, if he leaves and comes back, why does she get older? Why does he get older and not her? Because from her perspective, he left and then went back. That's weird. And he does a very good job of explaining this. It's called the twins paradox of like, why does one twin get older just because they leave and come back because of that whole scenario. I think what gets people caught up is the idea that they left Earth and came back. But the same is true of you were flying through space at who knows what speed, and then you had a shuttle branch off to go check out a nearby planet and then come flying back, or a nearby star and come flying back. That guy would be significantly younger than everybody who stayed back on the ship, even though compared to Earth they're all still moving that way. And then the question then becomes like, well, even though the guy who flew off, yeah, he left, but according to his perspective, the ship got further and further away and then got closer and closer and closer. So it depends on how you want to reframe it, but it still comes down to the fact that just because one person leaves, why does that person get to be the person that stays young? And so looking at these scary equations, so the top one is a way to track movement and time in relation to each other. When you break that math down, they can give you the comparative duration towards each other, and if you combine those two equations, you get the simplified thing. Yes, simplified. So, let me bring my scrolling screen up. When you look at that last equation you get this. And the easiest way to explain it is you have the time according to the person who went on the travel, who moved, compared to the person who's stationary, their relative perspective of time, over this variable number gamma. Seeing how gamma is just a number, and t is a time, and the other one is a time, there's no, when the math resolves and you start to cancel it out, like you have time on this side and time on this side cancels out. You have distance on this side and distance on this side cancels out. When you get all done, there's no variables left in the equation. So the question becomes, well, if time doesn't determine the fact that somebody ages that while they're traveling, and distance doesn't necessarily determine aging, what determines who ages? And ultimately, the only difference between the scenario of person A and the person B is that person A never changes their point of reference. Person B does. It is solely the act of moving from one point to another relative to a different person that causes the change to happen. Because yes, even though person A is moving relative to person B because they're getting further away from B, A is still in, according to them, in one spot, whereas person B is clearly moving from point A, from a certain point, and then back again. It's weird that all it takes is a point of reference change, the act of moving. So in short, as long as you're moving, you'll stay younger. So go exercise, folks. Thank you. This has been a PSA for the YMCA. But that was really weird. That was weird to realize too, is because when all the math resolves, you don't have anything about time, you don't have anything about distance, you just have a flat number. So the only thing that actually is different between person A and person B is the fact that person A doesn't change their point of reference in relation to themselves. Who knew? The fact that chat's quiet makes me feel like either one, everybody left, or two, everyone's going, or three, people are like, whoa. But let's, now that I've gotten done with the lecture part, we're going to do an example that will make it make a lot-ish more sense. Fucking hate math. Science is fascinating, and I hate math. We're gonna do math. I've already written out all the math. I was gonna do multiple examples, but I realized that the multiple examples just became redundant, and I didn't feel like making a graph. But we'll do one example. And like even when I was trying to explain this to myself, it was really hard and confusing. But when we let me flip to this next screen. What we're gonna do is we're gonna do an example of what would happen if we flew to our nearest star and came back, because we can relate to that, right? So we will get to that in just a moment. But yeah, when I was trying to do the math, and I finally sat down and I pulled up the data, and I found out what these distances are, and I calculated it out and started plugging them into the equations, and I saw the things start to play out. I went, oh, this is making more sense. It's making more sense. This is really cool. Okay, I can actually take these things at face value. Speed of light doesn't change. Cool. I'm just doing my nails. So we'll go ahead with an example. I've got literally 4 beverages here, and I can't decide which one to drink. We'll keep with iced tea for right now, because we can hydrate and it's caffeinated. So, does anybody know? Don't look at the screen. Does anybody know what hostage? Oops, wait. What are those drinks? Well, drink 1, water. I haven't touched it. Water is boring. I don't like water. Why drink water when I can drink tea, which is about 98% water, and then tea? So I have unsweetened tea. I don't like sugar tea. They usually put too much sugar in it for me. I'm sweet enough already. So there's that. Speaking of sweet, the other next drink I have, we're saving this one for later, is this is a triple shot energy Starbucks coffee, caramel flavor. That sounds tasty. And this is probably what you think it is. This is a got quite the bouquet. It's a is a red wine. It is a very good red wine. It is Gothic Inferno, and it is, selling point behind that is it is aged for I think 60 days in a whiskey barrel. So I vote you finish the wine, drink some water, then the coffee. No, I was kind of going to go the other way around. That's my input to stream. I figured the caffeine would have to keep me like energetic, and then the wine would smooth me out. Anyways, so we're going to go ahead and do an example here with our nearest star. Our nearest star is called Proxima Centaurus. Of course, we all know where that is, right? I found a map. That shows where it is. It's in the middle of the Centaurus constellation. Derail successfully. I hate you. But I had to look up where this was, because like where I live, when I look up in the sky, I see the Big Dipper and the Little Dipper, and this time of year, if I look in the south sky, I see Orion. If you were on the bottom part of the planet, or looking south, you'll see the Centaurus system, where you'll have Alpha Centauri and Beta Centauri, and then Proxima Centaurus. The reason why it's called Proxima is because it's the closest in proximity. But I know that also doesn't really give you the best angle, so I pulled up a screenshot. So Bottom of the planet. It's just right there. It's right there. You can see that, right? Just right there. That's where it's located. That there. So the star's right there, as you can clearly see. So we're gonna do the math to figure out what would happen if one person stayed on Earth, another person traveled there, and then came back. So simple enough. As you can pinpoint the planet here, maybe this will help. It's right there. There. Yeah, that one right there. So you have Alpha Centauri and then Proxima. So there you have it. That is our closest planet, or our closest sun to us. It is 4.25 light years away. That means the amount of time it would take light traveling at 300,000 kilometers per second. It would take light 4.25 years to make it all the way there. If you flicked on a lighter right now, that light would theoretically make it to that star in the year 2025 and a half. Isn't Orion the one I thought looked like a frog? Yeah, I can see why you would say that. Because you have the belt, and you have it goes off in 4 different directions like a frog going, blah. Anyways, it's in the constellation Centaurus. It's the sun in question is 0.123 solar masses. Everything in science sounds kind of scary, but when you realize that we just base number 1 off of us, it means that sun is about a tenth of the size of our sun. Our sun is 1.0. Same thing with radius. Our sun is 1.0. The radius of that sun, and radius is from the center to the surface, is 0.14. So about 14% the size of ours. So roughly the sun is basically, this sun is roughly 1/8 the size of our sun. But the fun thing is, it has 2 planets surrounding it. I didn't not check to see whether or not either of those planets would qualify as potentially being able to sustain life. I didn't have time, and it was irrelevant for my testing. But yeah, so that's our closest planet from us. The question is, how long does it take us to go 4.25 light years away if we don't mess with relativity? Well, what do we got going for us so far? So far, we have this little thing launched out back in crap, was it in did I write it down somewhere? It didn't. We have, yes, it's an M5. You'd think that'd be an M1, but I think I can't remember what year they launched out. I want to say 74. But you have both of the Voyagers way back when we were in the middle of the space race with Russia. We launched out back in the 60s and 70s. We launched out 2 probes that were going to do a sweep past some of our outer planets, take our first photos ever, and then just continue on into space. We have Voyager 1, Voyager 2. Because they're going on voyages, and because we made 2 of them. And they are equipped with all sorts of data on them regarding diagrams as to the human, that old classic Da Vinci drawing with the man and the woman drawn like this with a circle, and then that classic diagram. I'm sure if you saw it, you would know it. Pretty much we basically gave them a blueprint of here's what we look like naked, and here's a breakdown of all of our different language symbols saying hello, we come in peace, just in case somebody happens to pick those things up. So Voyager 1, Voyager 2 are set to roughly go into those star clusters, which mean nothing to me. They're super far away, 19 light years away roughly, so they got a ways to go. But they've been traveling for about 40 years now. I honestly, up until a few years ago, I just assumed that after they made their trip, they died in space. Because I mean, my phone's not going to make it to 2022. Why would Voyager make it 40 some years later? The fact of the matter is, both of those, at least Voyager 1, I didn't check Voyager 2, but at least Voyager 1 is still broadcasting. It's still collecting data, and it's still sending it back. But the problem is, the further away it gets, the longer it takes those radio signals to make it back to Earth. But it only collects data in the direction in which the dish is facing. So when the dish faces forward, if it hits with a side wind, it doesn't pick anything up. But if it turns the dish towards the wind, then suddenly it's just picking up tons of data. Now, the question becomes, how far are they so far? And they've been traveling for quite some time. They're pretty far out there. There is something, if you think about the sun as radiating heat, and that's like a force field almost, because it's pushing energy out, there's a point where the heat of the sun is pushing out, but all the cosmic energy of the combined suns radiating this way end up hitting this wall, and that's the heliopause. That's where, and the terminal shock, that's what that boundary is. It's where the sun's outward radiance no longer is the primary influence of something traveling. And to the best of my knowledge, Voyager 1 has finally, 40 some years later, just cleared it. It is technically finally the first thing we've ever made to enter interstellar space, outer space, like that space between stars. Ichi, you wrote something really long. I'm not going to read it right now because that looks painful. I want to finish to explain what I'm explaining here, but I will get to that. So Voyager 1 and Voyager 2 are still on their way out. But let's pretend real quick that Voyager 1, instead of drifting off towards galaxy to the interstellar cloud that has GJ 686, instead of that, let's pretend that they launched Voyager and it's headed straight to Proxima Centauri. And so here's what we get. This might blow your mind, but Voyager is currently traveling at a speed of 17 kilometers per second. Let me do a little bit of that math for you, because I need to convert that. For us silly Americans, they're not going to do that the easy way. Wow. So 17 kilometers per second. 1, 2, 3. Is roughly 38,000 miles per hour. It's going pretty quick. What is that conversion just in general? Okay, so 17 kilometers per second is 10.5 miles an hour. Or 10.5 miles per second. So if you can picture something that's 10.5 miles or 17 kilometers away from you, Voyager 1, this piece of junk that has basically just a dish, is flying through space fast enough to go from whatever point you just thought of to, that's from where you are to that point 17 miles away in 1 second. And even at that speed, if you break down the math to figure out what that is for the distance to travel there, it's painful. So Proxima Centaurus, its distance is 4.243 light years away. I gave you the astronomical units, the AUs, which is another mathematical symbol that you don't actually need, but for math and science nerds, it's there. But what it equates to is that number, which is, what is that? Hundreds, thousands, millions, billions. So it's 40 quadrillion 208 billion kilometers away. at the speed that the that Voyager 1's going, if it was headed towards that star, it would get there in about 75,000 years. Which means if it went there and then came back again, it would take it 150,000 years to go there and back again. Like, we'd have dinosaurs again, assuming we still even had a planet at that point in time. Don't know if it's still going to be broadcasting at that point. But you can see how even something that's traveling at that ridiculous of a speed, even if we can make a ship and go that fast, we're never going to get to our closest neighbor, like, ever. No, period, no. The human race hasn't even been around for 75,000 years. I think 10,000? I don't remember what the exact number is. Okay, what did Peachy say? Spoke way too confidently. Proxima Centaurus B orbits the star at a distance of roughly, ouch, yeah, 0.05 AUs, with an orbital period of approximately 11.2 Earth days, and has an estimated mass of at least 1.2 times that of Earth. It is subject to stellar wind pressure more than 2,000 times those of Earth from solar wind, is habitually has not yet been, its habitability has not yet been definitively established. Okay, well, something going that fast is probably not a good spot to be. So what Peachy just said was that, let me explain this real quick. In a 1 AU, so if you look directly above me, I wrote down that Proxima Centaurus, that star, is 268,770 AUs away. 1 AU is the distance from Earth to our sun. So if you take that distance and you times it out by that number, that's how far you have to go. But if you think about the fact that the Earth is 1 AU away from the sun, exactly 1 AU away from the sun, the planet one of the planets surrounding Proxima Centaurus, like that one in that video, that animated one, is actually 1/20th of the distance from what Earth to the sun would be. And it's it's going pretty fast because it's also 20% bigger than Earth, and it goes around the sun every week and a half. That's intense. That's fun. This is what I love about the math and stuff. It's painful. So let me get back to my slideshow things. Peachy, thanks for looking all that up. So now the question becomes, what if we are going at the speed of relativity? Back to our original topic, what does relativity do to the game? What happens when we start to get towards light speed? So first off, just to clarify, in terms of light speed, how fast is Voyager traveling? And if you do the math, because light speed is that 299,792 kilometers per second, in comparison, Voyager is going 0.0000567% the speed of light. It is nowhere near in the range of how fast you need to be going for light speed relativity to even matter. Even at 38,000 miles an hour, speed of light relativity doesn't even come into play. You need to be going way faster, way faster. You have to be like hundreds of thousand miles or kilometers an hour. Or a second, not even second, an hour, a second, for relativity to come into play. And that's where the Lorentz transforms come in, and this is where it starts to look really scary. So, the Lorentz transforms, and I fully expect you over between this slide and the next slide, I expect your brain to hurt. This is kind of for the people who geek out on this. I will then simplify it afterwards. So if you're trying to figure out, like, if I stay on the Earth and we send a ship out and then it comes back and it has a cute little kitty on it, this is what the equation would look like. So you have the time moving and the time stationary divided by gamma. Well, what's gamma? Gamma is just a number, and that number is determined by 1 divided by the square root of 1 minus velocity squared divided by c squared, which is blah, 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 blah. You can see that hurts. I get that. I totally understand. So, but if we take that bottom equation, we can actually plug numbers in. So we know what the distance is. We know what the speed of light is. So we can get rid of all those variable numbers. And what that leaves us with, because we know what D is, because we have a set D location, because we know how far away that star is, and because we know what C is, because the speed of light, again, is constant and it never changes, the only number that determines what gamma is T, the amount of time it takes to travel. So if I skip back to this real quick, essentially the difference in age comes down to that. So to read it back out, this is like, no, what did I write for myself? Normally the equations would look like this. This is painful. The one reassuring thing is that when you break it all down, all you need is a time duration input to determine gamma. In our example, it looks like this. So let's look at this in an easier example. So to make it easy, here's your, going back to the equation. That's the equation before we broke it down and got scary. Another way of looking at it, instead of typing in all these big scary numbers, a different way we can look at it, I thought I liked math. You will like math again in just one moment. Instead of looking at this and this, you can take that first equation and realize that v, velocity, what we're talking about is trying to approach the speed of light. So essentially, v is just a percentage of the speed of light. So, because we're going to be talking about like, well, what happens if we're going at 80% the speed of light or 90% of the speed of light? Then the equation gets a lot simpler. And it looks like what it does at the bottom. So now that I've again continued to explain this in scary fashion, let's make it real for people. Here, I got an example. Ready? So let's talk about going to that star and coming back. So in this scenario, let's say that GatorStumps travels to Proxima Centaurus at 95% the speed of light. Meanwhile, Hostage stays on Earth and streams the whole damn time. Again, let's remember, travel distance is 4.25 light years, the amount of distance it would take light to travel to Proxima Centaurus. So if we do that math, so we take that equation, which, let me skip back. So that equation at the bottom where I made it just based off of the speed of light, where it's a percentage of the speed of light. Hey, Mermaid showed up. Mermaid showed up at just the right time for this. So we are breaking down. We're breaking down traveling at light speed, and you like, for anybody who's seen movies like Interstellar, you know that. Thank you for the follow, and the host, Autumn Lover. Autumn's a good time of the year. What we're talking about for our science lectures, we're going into talking about how when you reach the speed of light, time slows down. So anybody who's seen like the movie Interstellar, you know that when they land on certain planets, everybody else back home ages a lot faster, and then when they see each other again, some people are super old, some people are super young. Carrie, thank you for the follow. Jane, welcome, man, welcome. Thank you for the follow as well. I still can't decide what I want to be drinking. Wow, long word. I'm not even going to. Something abstract. Alvarado abstract. There we go. Aw, Carrie, thank you. Mermaid, how was your stream? Peach just hosted because she knows what we're about to do. So we just spent a while going through. We're talking about what's gonna happen if we were to travel to this near. Well, let's go back one screen. I'm going to skip through a lot and make this a lot simpler for people. So Proxima Centaurus, the orange one on the map, that one is the closest star to us. You can see it in the southern hemisphere. According to Earth, it's right about there. Yep, right about there. To make it even simpler, everybody likes animation. It's right there. There. So for mathematical example, we're going to show what happens if you're going at 95% the speed of light, what the difference is between a person who lives on Earth and a person who goes to light speed and then comes back. For anybody who wants the full breakdown of what we've been talking about, I don't know whether or not it's digestible. I've just been talking about it. But the beginning of this stream, and I'll even crop this later on, I go into explaining why light is a constant, and then knowing that it's a constant, how they figured out that time would change. And then we got into talking about what the equations are. Now the equations are that the equations are super duper scary, and we've been flipping through them, and then I've tried to make them simpler, and now we're at the point of doing an example. So here's our example. Hey, we got a hype train, Zoe. Thank you for gifting a sub. Everybody, like, stream was great, so happy to be here. Happy 3 months. Yay, thank you. I can't even keep up with the alerts at this point. So here's our example, guys. GatorStumps, I'm going to travel to that planet.
I like that boulder.
That is a nice boulder. I'm going to travel to Proxima Centaurus. I'm going to go at 95% the speed of light, which is a ridiculously huge number we'll look at in just a moment. Locke! Welcome in, Locke. How have you been? We're going to travel at the speed of light. Or I'm going to travel at the speed of light. Hostage, meanwhile, is going to stay on Earth. He's going to stream video games the whole time. So we break down the math. We're going to take that equation there at the bottom. To try to figure out what gamma is, because gamma is the only thing. Well, I stay on Earth and stream the whole time. Is that a read? Oh, you're right. Whole should have been in italics, like the whole time. So let's do the math. So if we take that equation I just showed you, where it's written in terms of the speed of light, what you get is at the top, you have Gator's going to be going at a certain percent of the speed of light over the speed of light. This is what Gator's going. This is what the speed of light is. This is what the numbers look like once you get rid of all the scary stuff and you let the math break down. You let the math break down, you do the exponents, you break it down more. This starts to look a little less scary down here. So that's what gamma is going to end up being. You do the square root, you take that, you do the subtraction, you do the square root. What you get is gamma equals 3.2. Well, 3.2026. Actually, it goes longer than that, but I rounded it off at that point. So now we have a gamma number. So if we take the time of a stationary object, hostage, and then we take the time of a moving object, me, and then we times it by gamma, that gives us our numbers. So what that means is, and by time I mean duration. So time moving is the amount of time it takes me to get to Proxima Centaurus. The time stationary, for the time for hostage, is the amount of time that elapses for him while I'm off doing things and he's sitting around streaming the whole time. So we break that math down. We need to figure out what Gator's time is. So Gator is traveling at 95% the speed of light. Break that down. How long is that going to take? So you have the distance he's going to travel, which is 4.25 years. You have the velocity. How fast is he going? Well, he's going 95% the speed of light, which this is the math. It's going to take Gator at 95% the speed of light. It's going to take him 4.477 years to get there. That ain't bad, given the fact it's going to take Voyager 75,000 years to get there. So now that we know that Gator only ages 4.477 years, let's see what happens to hostage in that time. In the same amount of time, when you take the gamma number, which we've figured out, and you times it by the amount of time I'm gone, hostage, in the time I only age 4.47 years, hostage ages 14.38. Hostage got old quick. So, breaking that numbers down, here's how it works. Conclusion. GatorStumps went to Proxima Centaurus at 95% the speed of light. Round trip took me almost 9 years. At that point in time, I would be 47. Yep, you can do the math. I would be 47. Hostage, meanwhile, sat around playing games. Oh, there we go. The whole time. And for him, he's been at it for 28.68 years. He is 61 years old. How's that feel, buddy? How you feeling now? Now who's young? Yeah, that's right. Gator is. That's me. Bogey. In conclusion, the closer to light speed, the slower you age. So, if Gator were to go any faster, hostage would be dead. This screen alone, this screen right here, this is what made me happy. This was the toiling and doing the math. Remember that one stream, Hostage, you were doing, and I jumped on. I'm like, Hostage, how old are you? And you're like, why? I'm like, I need it for research reasons. This is why. This is what I was doing. There we go. So, too bad, so sad, the end. Bye, Hostage. We got questions? That's right, I remember that. It's like I'm trolling, but it takes like 2 weeks to come back to you. It's great. Although it's 2 weeks actually for me it was only like immediately because I did it right then and there. For you, it took 2 weeks. Look at that, it's almost like the travel light. I feel like I made sense. Did that make sense? Choo choo! Ooh, I received a hype train. Guys, again, thank you for the 3 subs, 100 bits, all that fun stuff. Ooh, what did I get? Oh, sweet. Oh, kick the door open. It made sense for me. Sweet. Now we can't give Gator any info because we'll be dead by the end of the research. No, I'm really glad. I'm really glad how this one turned out. I did do a previous one on just how black holes worked. And I tried really hard when talking about black holes to not get into time dilation because I knew that would be a whole nother conversation. But if you go into my highlight videos, I do have that lecture, and I'll make sure that I crop this one afterwards so we have that one as well. But